Hello and welcome. This is part one of two. Part one is talking about what is astronomy and how do people identify a coordinate system in the night sky. Part two will be me actually going outside and looking at the things that I am about to tell you about. So let's just get right into it. So the two ways that people do coordinate system is right ascension, declination, and an azimuth grid. I can explain both to you. Let's start with the azimuth grid. If you look over here, right? Look over here, you'll see the giant zero. That is, imagine you are on the surface. You are looking out to the horizon. That is zero, right? And then from zero you go up. It's 5 degrees, 10 degrees, 20 degrees, right? And it keeps going up and up and up until eventually you get to 90 degrees. And 90 degrees, if you imagine zero and going up, 90 is straight up, right? So if 90 is straight up, then going down is negative 90, right? And that makes sense because in algebra, 180 degrees is a line, right? So if it's 90 degrees this way, then 90 degrees this way. Makes sense, right? So that is that direction, right? But now it's this direction. So facing north, right? This goes from 0 degrees to 90 to 180 to 270 and then 360, right? So that's that and then that, right? Actually, let me put it like that. So you could say any direction like this. You could say like 90, 80, right? Because it's going 90 degrees, 80 degrees. And that's straight true up and down, right? But the reason why azimuth grids, although they're simple, they don't work well, is because if you were right, I don't know, if you were like in New York and said 90, 80, that measurement anywhere else in the world does not make sense. It only makes sense to you right there, right? But in science and astronomy, you want to be able to confirm your work with other people. So that's why the majority of people use the right ascension declination because it can be determined because it can work with anybody on our planet. Sorry, anybody on our planet, right? So even though let's get out of like 2D thinking of like up and down. Let's think outside the box. Like for example, Earth is axis tilt. Earth has an axis tilt, right? And that tilt is exactly 32.5 degrees, I think. And imagine a line going straight up and down through that, through our planet, right? That is the line of axis, right? That line of axis just so happens to be at a pure luck where Polaris is, right? So if you look at a star map, and and if you have Polaris, let's start with declination, right? You start at Polaris, that's 90, and then just like the azimuth grid, it starts at 90, 80, 70, 60, 50, 40, 30, but it's not from the horizon, it's from Polaris, right? Because Polaris is north, and north is the line of our axis tilt, right? So that is declination. So if I said 80 declination, it would be in this circle, right? But right ascension is different because in a coordinate grid system, you need two factors to locate any point, right? So the other factor is not measured in degrees, but it's measured in time. Because there is 24 hours in a day, right? Because our Earth is rotating east to west, the degrees is not degrees, is replaced by hours, right? So it's 0, 6, 12, 18, 0 slash 24, because they actually mean the same thing. So for example, if I said, using the grid system, if I said 1380, right, you would see this and go to 13, so somewhere in that line, and then 80, where that intersects that, so you know you'll be talking about that star right there, right? And the reason why people use this is that you can be anywhere on the planet and say this measurement, and then anybody else on the planet can see that measurement and point to the same exact part of the sky, right? I know that was a lot, but that's the basic gist of it. I even made these little fun notes. Ooh. You can see our Earth, right ascension and declination. That's North Pole. And that's the celestial equator, right? Fun notes. So that is the coordinate system. Now let me talk about what we're actually looking at. So of course, I know you know the stars, but let's talk about the magnitude for a second. Magnitude is the brightness is the brightness of the star, and you might think that it's that the bigger the number, the brighter it is, but it's actually negative, right? So -1 is actually brighter than 1, right? Brighter, dimmer, right? But here's the thing. It's not just linear, like 1 is brighter than 2, and 2 is brighter than 3. It goes exponentially, right? So if you have 0, by the way, the 0, like, imagine the coordinate 0 is, if you have any point on a grid, it's only relative to something else, right? So in this case, this whole grid system is relative to Vega. Vega is 0, 0 brightness, right? So if you say negative, it's brighter, and positive numbers is dimmer, right? For example, a full moon is -12, and it exponentially gets higher. What I mean by that is that if you say 0, you're talking about Vega, but if you say 6, it's not 6 times brighter than Vega, it's 100 times, because it exponentially gets more and more and more, right? To put the exponential curve in example, the sun is -32 magnitude, so that gives you a little bit of scale, right? And then that is, well, that. Now let me show you some of the things I've personally actually done myself. So I've done a lot of astronomy, and I have got these pictures from my telescope and printed them out, right? So you can never truly know magnitude because something could be farther away and brighter or closer and dimmer, so you can never truly know the size, but you can simply see how bright it is. So here is a picture of Sirius and Betelgeuse, right? And right off the bat, you notice that the color, by the way, it was really expensive to print these because it's all black, and so I was really thankful that I got them printed, and they look all nice. Oh my gosh. Anyways, you notice that they're different colors, and different colors have different wavelengths. What I mean by that is, an example of this is, have you ever been in a fire, well, not in a fire, watching a fire, like a fireplace, and if it gets really hot and it turns blue? That's because it's producing a higher wavelengths of light. And what that means is that our eyes can only detect a very small sliver of the whole spectrum of light. And so when something burns hotter, it has a shorter wavelength as something that burns slower. And slower wavelengths is example as red. Your eyes perceive that color as red. And then the shorter wavelength is blue, right? And you can also see that if something's a shorter wavelength, it's physically smaller. If something is physically smaller, right, that means the thing is physically smaller. So that's why you can physically see that Celsius is smaller than Betelgeuse, right? So that's really cool. You can really just see the color just pop on that. This isn't any filtering, not like changing like the saturation or stacking photos on top of each other. This is just the pure star, right? And here are some other fun pictures, like Saturn, for example. You can see this is when Saturn rings were in parallel, so it looks like a straight line. I don't know. That just looked really cool. And then another galaxy is M51. Um, I did want to talk about the nebulas and how we name things. So all nebulas, well, uh, a lot of the nebulas start with M as in a number to describe what it is. For example, Meslar 51, right? And then there's Meslar 50 and 49, 48, 47, and it goes on and on and on, right? And the thing about this is that you might not know what these two smudges are, but those are actually two galaxies colliding. So that's really cool. It's most commonly known as the Whirlpool Galaxy. Um, but yeah, and every galaxy has its own subclass and a name. It has its like official name like M51, and then it has its unofficial name like the Whirlpool Galaxy because that small galaxy is colliding with the bigger galaxy. And by the way, all this was done on my telescope myself, so that's why it's probably not the highest quality photo, but still, I'm proud of it. Anyway, hope you enjoyed watching this. I will see you outside.